Next topic is the Landsat series of satellites that was launched by the United States, specifically the NASA, with the cooperation of the US Department. They had done the launching of the Landsat series 1, 2 till 5 for the first generation, and they had been a part of the Earth Resource Communications satellites that was being deployed in space for monitoring the Earth. So the NASA, with the cooperation of the United States Department of Interior, began a conceptual study of the feasibility of services of Earth Resources Technology satellites. So this was launched in the year 1972 on July 23. So this represented the first unmanned satellite specifically designed to acquire data about Earth resources on a systematic, repetitive, medium resolution, and multispectral basis. This was primarily designed as an experimental system to test that feasibility of collecting Earth resource data from unmanned satellites where people were not being present. From that, how it acts or how the data signals are being captured and sensed. So just prior to the launch of the Earth Resource Technology Satellite B, NASA officially renamed the ERTS program as Landsat program. So all the subsequent satellites in the series carry the Landsat designation. So far, 5 Landsat satellites have been launched successfully by NASA. So the characteristics of the Landsat series missions will be explained in brief. So there have been 4 different types of sensors that are being used in various combinations on these missions. So let us see them. So the Landsat took images. The first one is the Seychelles Island. See the Seychelles Island, how it is being present, surrounded by water. The Landsat image is taken over the bands 3, 4, 5. You can see here the red color, not the top, bottom. You can see at the bottom. You can see at the surrounding we have the water bodies which are being green color, and we can see the islands with coral reefs. So bands 5, 4, 5 reflected. Sorry, 3, 4, 5. The spectral bands of 3, 4, 5 was being used in the Landsat images, and they gave resolution like this. So the white represents your mountains or peaks, the red represents your desertous regions of the Seychelles Island. So you can see the top is your Amazon river, Amazon forest, where it is present in Brazil. It is used for monitoring forest clear cutting. You can see the first picture, which is at the left side, has more vegetation. You can see the greeny structures are vegetation. So the flow of water is in brown color. You can see this dark gray brown. So this goes. So this is your flow of water. And after a few years, you can see that the vegetation, the trees has been cut down. The forest has been cleared. So you can see only this part is available. So this part is available, this part is available. Here all the flow of water, the structure is not changed. The structure of the river, of this river, is not changed. But in and around that, the vegetation which was found is being cut out. So forest clearing can be easily monitored by using the Landsat images. So the Landsat TM and ETM plus. Okay, TM is your thematic mapper, external thematic mapper plus. Okay, so 4 and 5 is a thematic mapper, and 7 is your extended thematic plus. So this is how the Landsat characteristics falls. It is sun synchronous type, inclination of 92 degrees, with an altitude of 705 kilometers above the surface of the Earth, with a temporal resolution of 185 kilometers, and the orbital period is about 16 days. That is 233 orbits. Is what width is 185 kilometers, and the sensor being used are thematic mapper, enhanced thematic mappers. So that is being listed here. You can see at the bottom. Blue band 1, green band 2, red band 3, near infrared 4, thermal infrared 6, shortwave infrared 5, shortwave infrared second part is 7, and we have the pan extended panachromatic resolution. So this pan is present only in the extended ETM plus. Okay, Landsat 7. Landsat 4 and 5 we have only this resolution. So if you use the blue color, it gives a resolution of 30 meters, green 30, all are 30. You can see only thing is that the thermal infrared gives a resolution of 120 meters. So we are already seen the wavelength of all the bands in the STS class. So similarly for Landsat 7 ETM plus, you can see the resolution is about 30 for all the cases except thermal IR, which gives 60-meter resolution, and pan gives 15-meter resolution. So this is how the Landsat is being launched in space. We have these sensors that scans the Earth's surface. The imaging scanner is present in the satellite. The solar panels generate electrical power and supplies to the satellite entirely. So a part of that is being replaced by the image scanner, and this is the Earth. Next is the SPOT satellites. So System 4D observation DLERA is the expansion of SPOT. So this SPOT satellites was being developed by French government in association with Sweden and Belgium. They undertook the development of System 4D observation DLERA SPOT, and it was convinced and designed by the French Centre National Aeronautical Space CNES. So this Spot 1, which was launched by the French government, was retired from full-time services on December 31, 1990. So Spot 2 satellite was launched on January 21, 1990, and Spot 3 was launched on September 25, 1993. Spot 4 was launched on 26 March 1998, where Spot 1, 2, 3 have identical orbits and sensor systems. So these are the specifications of Spot XS1. So the Spot is the satellite or sensor being used. The bands and wavelength are being configured here as X-band, S1, S2, S3 and S4 in different wavelengths, with a spatial resolution of 20 in all the cases except for the monospectral red. You can see at the bottom you have a monospectral red band, which uses 10-meter spatial resolution. Then the swath width for all is 60, having an oblique skin at maximum 60 by 81. So the reputation coverage of this Spot satellite was 26 days, where the orbit altitude is being kept at 822 kilometers. So the launching periods was varying. You can see 1986, 1998, 1990, 1998 and 2002. The characteristics of the Spot. is being given. The type and altitude is sun synchronous 832 kilometer. Inclination is 98.7 degree, 101 minute and 26 days. (26 days) is the orbital period. The swath width is 185 kilometer and the sensors are high resolution which are in visible spectrum. You can see the spot HRVs, band used in multispectral XS1, XS2, XS3, and its typical resolutions. So 0.5 to 0.59 green, measured in micrometers, 0.61 to 0.68 micrometers, red 0.79 to 0.89 in near infrared region and 0.51 to 0.73 in the visible region. Next is the spot panchromatic mode with 10-meter resolution. You can see how the area looks like. Here the lightish are having higher temperature, the darkish areas are having lower temperature. So from this we can identify that this represents that the place is cooler, this place is cooler and this place is warmer, and these has the other places has moderate temperature. So spot multispectral mode using the uh, RGB color combinations red, green and blue. Here you can see that how the spot XS1 looks, same picture in green band, how it looks in red band, how it looks in infrared band. Okay. From this you can able to understand how the green band works, how the red band works and how the infrared band works. So since remote sensing is all illustrative in nature, I can show it only with examples of this. For the same area, if you take a false color composite, you will get like this structure, false color composite. And if it is a natural color composite, it will look like this. Same area. All these are same area which is being taken in different bands. So any queries in the Landsat and Spot, you can type in chat box such that we can proceed further into the IRS, Indian Remote Sensing. Any queries, type in chat box. Yeah, answering to the question of Sai Ganesh, I'll complete first Sai Ganesh answer. In the last slide, what the blue color indicates. So the I'll show you. So the blue color, as you see in a so as you can see in the green band, the same picture is being spotted out. The same picture is being spotted out. You can see this line. So this is what you're able to see here in blue, right? So in green band, it is going like this, like a snake structure. So here it is also the same snake-like structure. Here it is going like a snake-like structure. You can see in IR band. So you can see here that in the false color composite, you can see that it has a blue color. So this is what you're asking, a blue color. So now you see it in original natural color, what it is. Original natural color, if you see what it is, it looks like a payment or a way of water that has been dried out. Okay, payment of a water body. You can see an canal-like structure or an river-like structure. Okay, you can see this. So this blue that is being going in this false color composite indicates that it is a payment for an water body. Okay, flow of water. The natural composite will give you the exact resolution. Got it, Sai Ganesh? And Sri Subhash, you had asked only by temperature how can they differentiate all the types of lands and water bodies? So for that you need to see the reflection properties. Okay. If you send an electromagnetic wave in that particular wavelength, it will reflect with an principle that we had seen. Just a minute, I'll show you that. Yeah. So these spectral bands and their potentials will identify you. Okay, band 1, band 2, band 3, band 4, band 5, band 6, band 7. All the an electromagnetic wave will be sent in all the spectral ranges. So if you get a response in the range of this, we'll be identifying it as water mapping or a soil vegetation differentiation or a deciduous coniferous differentiation. Okay, keep in mind this is a thematic mapper. So thematic mapper principle is dealing with temperatures. This thematic mapper comes from your thermal images. So for analysis, an image of relative radiant temperature thermogram is dissipated in gray levels with warmer temperature shown in light tones and cooler temperature shown in dark tones. You can see an imaginary which portrays relative temperature differences in their relative spatial locations are sufficient for most applications. So this principle is being used in your thematic mappers with the help of this spectrum. You can see the spectrum. So the wavelength is 0.76 to 0.90 micrometers will be used for biomass surveying and water body delineation. So depending upon that, we can, depending upon the spectral response curves or spectral reflectance curves, will be able to differentiate land and water bodies. Yeah. Thank you, Sri Subhash. Okay. So any other queries you can type in chat box. So that blue color in the last slide that you're quoting, Sai Ganesh, is a water body pavement, the flow of water. Okay, Sai Ganesh, thank you. We'll proceed on to the next topic, Indian remote sensing. So the Indian space program has the goal of harnessing space technology for applications in the area of communications, broadcasting, meteorology, and remote sensing. The important milestones crossed so far are the Bhaskara 1 and 2, which are the experimental satellites launched during 1979, which carried television cameras and microwave radiometers. The Indian remote sensing satellite was the next logical step towards the national operational satellites that directly generates resources, information in a variety of applications such as forestry, geology, agriculture, and hydrology in the Indian Ocean. So the IRS 1A or 1B carried linear self-scanning sensors, which is LISS. In some places, I would have quoted LISS, linear self-scanning sensors, which used linear type of arrays, the CCD arrays. In LISS 1 in 1A, LISS 2 in 1B. So in subsequent, the IRS P2 was launched in October 1994. Then an indigenous launch was done in by the ISRO at the Polar Satellite Launch Vehicle D2 in October 1994. Then the Indian Remote Sensing 1C was launched on December 28, 1995, which carried improved sensors like LISS-3, Wi-Fi SFS, and pan-chromatic camera. The details of the IRS series platforms are given in the subsequent slides. So this IRS P3 was launched into sun synchronous orbits by another indigenous launch vehicle, PSLV, from Sriharikota, which is present at Nellore. From the Indian Space Launching Station, SHAR. Then the IRS 1D was launched on 29 September 1997. Following, IRS P4 was launched in May 1999. So this is the table of the IRS Indian Remote Sensing versions 1A, 1B, 1C. You can see the number of bands being used in IRS 1A is 4 with no spectral range, a resolution of 72.5 meters, and the swath is 148, and the revisit days was 22. With type of sensor being used is LISS1 with multispectral, along with the LISS2 having a resolution of 36.25 meter with a swath of 36.25, and revisit days is same 22 days. Then in 1991, the IRS 1B was launched with the LISS multispectral bands 4 in the spectral range of these 450 to 520 nanometer, 0.52 to 0.59, 0.622, 0.68, 0.77 to 0.88 micrometers. All these three are in micrometers with a 72.5 resolution, 148 swath period, and 22 revisiting days. Then in 1995, IRS 1C was being launched with WIFS multispectral system with 2 bands as shown, with 189 resolution and 810 swath period with 5 revisit days. Then LISS 3 with these 3 bands, 0.52 to 0.59, 0.62 to 0.68, 0.77 to 0.86 micrometers with a resolution of 23.6 with 142 swath and having a revisit days of 24 to 25 days. Then another band with one band 1.55 to 1.70 with the same resolution in 148 periods, swath period 24 to 25 revisit days. So since we had seen that IRS 1C is being deployed with the pan-chromatic camera with 5.8 meter resolution with 70 swath period. Then following that is the IRS 1D, its specification, which is deployed in September 1997. With all the 3 is being deployed in that. WIFS, LISS3, PAN. Number of bands 2. Spectral range 0.62 to 0.68, 0.77 to 0.86, resolution 189, swath 774, revisit days 5. LISS3 with the types 3, number of bands 3, spectral range 0.52 to 0.59, 0.62 to 0.68, 0.77 to 0.86, resolution 23. SWAT 142. Revisit days 24 to 25. Panchromatic type is MS. Number of bands is 1. Spectral range is all over. So resolution of 6. SWAT measured in kilometers 70. Then in May 1999, IRS P4 was being launched with optical sensors, multispectral, number of bands 8 in this range with resolution of 360 with a swath coverage of 1420 kilometers and revisit days of 2. Then they had used radar type MSMR micrometer, microwave radiometer in these 4 bands 6.6, 10.65, 18, 21 gigahertz, and each operating at a resolution of 180, 80, 40, and 40 kilometers. With a swath of 13,360 kilometers. So this is an example of IRS, which is a sun synchronous with altitude of 817 kilometer, inclination of 98.69 degrees, 101 minutes, orbital period of 24 days. The LISS is your linear imaging self-scanning sensor. PAN is your single channel panchromatic. WIFS is your wide field sensor. So the PAN sensor is in band 1 with wavelength of 0.5 to 0.9 micrometer, giving resolution of less than 10 meters in IR S1C and swath of 705 kilometers. Then LISS band 2 0.52 to 0.59 green wavelength with 23.5. Similarly, band 3, band 4, band 5 green, red, near infrared, and shortwave infrared. Resolution all has 23.5 with a swath of same 142. Then wide field sensor operating in band 3, red, and 4 gives a resolution of 188 meters with a swath of 810 kilometers. So this is the image of an IRS photo being taken at different places. One is IRS fusion pan plus LISS lands. So this is photo taken by that. You can see how this greeny structure goes. You can see gray structures, green structures, ash type structures, green colors, and IRS LISS took photograph in the airport in Frankfurt. You can see this is the airport in Frankfurt. The Indian remote sensing LISS took photos and it appears like this. And the IRS wide field sensor took the photograph of Greece and Turkey. It looked like this. So these are some of the examples or images of Indian remote sensing which has been captured. Then there are other current satellite sensors that are being deployed. They are ALOS, GRACE. ALOS is the Advanced Land Observation Satellite, whereas GRACE is the Gravity Recovery and Climate Experiment, which have been deployed in space for specific application. So ALOS example, you can see how the ALOS is present. The main characteristics is that it was launched in 2006 January, and it was lost in April 2011. The main orbits that it revolves is that it is a sun-synchronous sub-recurrent orbit with a recurrent period of 46 days and subcycle of 2 days. Altitude, it was positioned around 692 km above the equator with an inclination of approximately 98.2 degrees. So this ALOS is one of the world's largest Earth observation satellite in size and has contributed to disaster monitoring and resource surveying in addition to mapping and precise land coverage observation. So this used PRISM, which is a panchromatic radiometer with the 2.5 meter spatial resolution. So the first image you can see, and PALSAR, which is an active microwave sensor for cloud-free and day and night land observation, which is a part of ALOS, which uses PRISM. Then we have the ANVIR 2, which is a visible and near infrared radiometer, which measures even in daytime and nighttime. Next is the GRACE, the Gravity Recovery and Climate Experiment. So this gravity recovery and climate experiment was specifically utilized for climate monitoring. This used a microwave link that connects the two satellites and makes extremely precise measurements. That makes changes in distance between the two satellites. These changes or fluctuations are caused by changes in the orbital motion of twin spacecraft as they respond to changes in the density of the surface that they're passing. So the density changes correspond directly to changes in the gravitational field. This is an example of a GRACE, how we took photographs. You can see due to an uneven distribution of mass inside the Earth's gravity field is not uniform, so that it has lumps. So this model greatly exaggerates the scale so that many small features can be seen here. See, you can see the Earth. This is the African continent. This is Asia continent, and you can see how the Africa looks at some parts. And this is Europe, how it looks. This is the GRACE model. Next is the IKONOS 2. So this IKONOS 2 satellite was launched in September 1999, and it has been delivering commercial data since the year 2000. IKONOS is the first of the next generation of high spatial resolution satellites that records 4 channels of multispectral data at 4-meter resolution. 4-meter resolution and 1 panchromatic channel with 1-meter resolution. So this means that the IKONOS is the first commercial satellite to deliver near photographic quality imagery of anywhere in the world from space. So IKONOS played a major role in communication of the satellites for remote sensing. So this had 4 bands in multispectral and 1 band in panchromatic with a resolution of 1 meter with a revisit days of 11. So this is the IKONOS satellite that was launched in sun synchronous with an inclination of 682 kilometer with a temporal resolution of 98.69, and the swath width of 11 days, and the system that was used in ICNOS is both across and along track scanning. So these four are the multispectral bands being used. Wavelength of 0.45 to 0.52 blue with a 4-meter resolution, 0.51 to 0.60 green with 4 resolution, 0.63 to 0.70 red with 4 resolution, 0.76 to 0.85 the near infrared region with 4-meter resolution, and the panchromatic P band 0.45 to 0.90 micrometers in the visible gave 1-meter resolution. So this is the ICNOS image being taken by the ICNOS satellite in two different places. The first one is a different place. This one is a different place. So this is being taken with an multispectral image with 4-meter resolution. Lunas Ares. Multispectral image with 4-meter resolution on the left hand side. Right hand side is the Sydney shipping yard with the panchromatic image with of 1-meter resolution in the right hand side. Next is an ICNOS imaginary sample with Boundbrook NJ. The upper, which is in gray white, is your 1-meter panchromatic resolution. The bottom is your 4-meter multispectral resolution. Multispectral band with 4-meter resolution. You can see this is your black and white. It seems to be a black and white or gray type, which is panchromatic. This is your multispectral. All the spectrum bands will be included in this. So any queries, type in chat box. If there are any queries, you can type in chat box. I'll give you some 5 to 10 minutes time. Then I'll proceed for the next part, which is part number 3. So unit 3 is divided into 4 parts. We had completed 2 parts. Then part 3 and part 4 is pending. We'll see that. Okay, since there are no queries, we proceed on to the next presentation in remote sensing unit number 3, which is based on radars. So unit 3 we had covered the satellites classification based on orbits, which is sun synchronous and geosynchronous. And based upon the service and application we had seen, the Earth resource satellites, Earth resource technology, the communication satellites, weather satellites, the spy satellites, then satellite sensors, its resolution in spectral, spatial, radiometric and temporal resolutions. Then we had seen about the multispectral scanning MSSS, its along track and across track sensors. Then followed in we had seen the sensors in Landsat, Spot, IRS and the current satellites available. So in the subsequent presentation, today I'm going to stand the radar. Okay, the basic equation for radar, what is radar, how it is being used in remote sensing, and the two different radars that are being used, which is side looking airborne radar and synthetic aperture radar in this presentation. So radar stands for radio detection and ranging, that you would have studied in your engineering physics. Radar. So this radar is using your microwave access electromagnetic field wave for measuring, ranging the targets which have been present on the ground. Okay. So there are two different radars being used deployed specifically for remote sensing. One is the sideway looking airborne radar and the synthetic aperture radar. So the sideway looking airborne radar measures the range to scattering targets on the ground that can be used to form a low resolution images. So whereas in a synthetic aperture radar, the same principle is being used as a sideway looking airborne radar, but it uses image processing to create high resolution images. So that is the difference. Okay. So now let us see the radar first. Then we'll see the side looking radars and the synthetic aperture radars further. So radio detection and ranging. This is your radar. So this radar is a ranging instrument, means measuring the distances inferred from time elapsed between the transmission of a signal and reception of the returned signal. So how much distance the time is taken between the transmitted signal and the reflected signal is to be measured. So depending upon that, we can find in what distance that target is present. So mostly this radar was used in military purposes in order to identify the tanks, enemies location, enemies missiles, enemies positioning and all. So that radar, which was developed in during the Second World War, has led into the monitoring of Earth surface also nowadays. So there are side-looking imaging radars which is used to acquire images with a resolution of 10 meter to 1 kilometer. Then we have the altimeters, which are nadir looking to derive the surface height variations. Then we have the scatterometers that derive reflectivity as a function of incident angle with an illumination direction and polarization of the radars. So the radar has three primary functions. One is transmitting, second one receiving, third one observing. So in transmitting, the radar transmits radio access signals or the microwave signals towards the target. Then it receives the portion of the transmitted energy which is backscattered from the target. Then it observes the strength or the detection and the time delay or the ranging of the return signal. So depending upon that, in how much distance that object or the target is present can be easily calculated. So this radar provides its own energy source and therefore it can operate both in day or night. So this type of system is known as uh, active remote sensing in active remote sensing. So this doesn't comes under passive because the radar itself will produce energy, microwave energy that is being transmitting from transmitter to receiver. So the principle of radar is this. Satellite can have the radar of microwave signals so that it transmits towards the earth surface. Then the earth surface will give reflection. So depending upon the return time or the returned energy signal, how much duration it takes, we can easily find out the object what it is. You can see a simple illustrative diagram. There is also the example of a radar. Swath is the period or the swath is the coverage of your platform of sensor which carries the camera or it doesn't or in radar it carries the coverage, and when it falls in a particular location on the earth surface, which we called as the footprint. Then we have the pulse durations which is being sent from the satellite for radio detection and ranging. So the amount of signals will be reflected back. So depending upon that, we can calculate the range of target. So this is an example of your AMI image mode geometry of ERS1 and ERS2 geometry for an radar detection, in which the mode SAR obtains strips of high resolution images approximately from 100 km in width and 250 km to the right of the sub-satellite tracks. So from the satellite, you can easily find out using your radar what is the target. So for that, we need to use specific wavelengths. So the wavelengths are being listed here. Most of the remote sensing radars operate at a wavelength between 0.5 centimeter to 75 centimeter. So let us see how they are being classified. They are being classified into X band from 2.4 centimeter wavelength to 3.75 centimeter wavelength, operating at a frequency of 12.5 gigahertz to 8 gigahertz is X band. And from 3.75 centimeter of wavelength to 7.5 centimeter of wavelength, operating at a frequency of 8 to 4 gigahertz is your C band. And from 7.5 centimeter to 15 centimeter, operating the frequency of 4 to 2 gigahertz. Then in L band, from 15 centimeter to 30 centimeter of wavelength, operating at 2 to 1 gigahertz. In P band, 30 centimeter to 100 centimeter, operating at 1 gigahertz to 0.3 gigahertz. So this is the operating wavelength of radar that is used in remote sensor. This is the electromagnetic spectrum placement. The microwaves are being placed P band, L band, S band, C band, X band, KU band, K band, Ka band, millimeter band, and the sub-millimeter bands. So that in the microwave bands of electromagnetic spectrum. So have a look over this. Then I'll continue in another 2 or 3 minutes. For queries, type in chat box. Since there are no queries, I further move on to the next slide. A comparison of the C band and L band SCR synthetic aperture radar. You can see L band resolution and C band resolution, how it is. So depending upon the need, you can use whatever the band we want. So frequency comparison, as of which band to choose in agricultural sector at Cleveland, Netherlands. The picture was taken by a radar satellite in L band region, C band region, and P band region. So C band you can see at the top, L band in the left side, same region, and P band in the right side. So the choice of wavelength. So for which application, which one we need to choose. So radar wavelength should be matched to the size of the surface features that we wish to differentiate. For example, eyes discrimination, small features, we need to use X band. For geology mapping, that is large features, we should use L band. For foliage penetration at lower frequencies with the higher resolution, we need to use P band. So in general, C band is a good compromise for all these bands. So new Airborne systems combine X-band and P-band to give optimum measurement of vegetation also. So depending upon the application, we need to choose which band for which application. So this is your radar working principle. A radar is essentially a ranging or distance measuring device that consists of fundamentally of a transmitter, receiver, an antenna, and electronic system to process and record the data. A transmitter generates successive short bursts or pulses of microwave signals at A, which is A as shown in the diagram, that are focused by the antenna into a beam B. Then the radar beam illuminates the surface obliquely at a right angle to the motion of the platform. See a spacecraft, sorry, an aircraft, not spacecraft. An aircraft is being flying. So the antenna receives a portion of the transmitted energy that is reflected or backscattered from various objects within the illuminated beam C. So C is your returned. So by measuring the time delay between the transmission of a pulse and the reception of a backscattered echo from different targets, their distance from the radar and thus their location can be determined. So for this, we'll be using two different radars. One is the pulsed radar, second one is the continuous wave radar. So you can see in the left hand side, time versus the near range versus the far range, how it goes. So the pulse radar sends pulses, and depending upon the returned pulses, we measure the time. So the round trip time for radar pulse is to get the target and return is being measured. So the distance is proportional to this time. In continuous wave radar, CW radar, the sender sends signals to the object and the object reflects back the wave, and the same radar will receive it continuously over distance. So this is the principle of ranging and imaging. So A picture is propagation of one radar pulse indicating the wavefront location at time intervals 1 to 17. So radar pulse is sent from the aircraft, which is dashed lines, and the returned is your dotted lines. You can see 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. At 10th, it reaches the target or objects. And then in return, it goes on. Okay. So return signal from the house, return signal from the tree. So the tree takes more. You can see that after 9, it reflects back. So 9, 10, 11, 12, 13, 14, 15, 16, 17 to the aircraft. So depending upon that, time intervals of 1 to 17, we can find the distance. So how do we find is that the return from the house appears within a short period. And see that within a short period, it returns back. But whereas from the tree, it takes a long period. So with the pulse strength, we can find it. So return from the house, it's having a peak at a very short period. So the distance is shorter. This means that the house is larger than the tree with an angle of inclination. You can see that. This is shown in radar pulse, is shown in larger diagram. So the fundamental radar equation is power received is equal to power transmitted, gain of the antenna in the direction of target. Sigma is the backscattered area of target. Lambda is the wavelength divided by 4 pi cube, the ranging distance, r power 4. R is the range distance from the transmitter to target. So this is the radar equation. So the wavelength ranges or the bands of microwave is being shown here. The same picture, I'm showing it in again. So here the K and Ku bands are very short wavelengths that are used in airborne radar systems, but it is not used nowadays. Then in X band, it is used extensively for airborne systems for military and terrain mapping. C band is used commonly on airborne research system ERS-1, ERS-2, and RadarSat. So then we have an S band that is used by the Russian Almaz satellite, L band used on onboard American CSAT and Japanese JERS-1 satellites and NASA airborne system. P band, which is the longest radar wavelengths that are used on NASA experimental airborne research system. So this K band and KU band were the ranges bands that were given in letters during the Second World War. So this is the band designations